There is a material that is replacing silicon in the most demanding electronics on Earth. For example, military radar, satellite communication, space hardware, even the fast charger on your desk. Well, this is gallium nitride. In short form, we say GaN. And today, what it actually is and why silicon cannot do what this material does, we are going to discuss. We have already seen that there are a lot of limitations of a normal silicon. For example, your phone gets hot under load and starts slowing down. Your laptop needs a fan running constantly. And old laptop chargers were very heavy because the silicon needed large circuitry to convert the power safely. Well, these are like the symptoms of the same problem. Silicon can only handle a limited amount of voltage and a limited amount of heat before it physically stops working. Well, this is not a design flaw. This is a material's limit, and it comes from one single property inside the materials. Well, that property is called band gap. It is like minimum energy needed to knock an electron free so that it can move and carry current. Well, if the band gap is narrow, electrons escape easily. This is good for low voltage electronics, but the material breaks down at lower voltage and fails at lower temperature because even heat alone can push electrons to loose. This was the property of a normal silicon. One more thing, silicon's band gap is like 1.12 electron volts. That is like a single number which is ceiling on the silicon. Every silicon cannot do the traces back to this. Now, another material, that is gallium nitride. This is a compound semiconductor. Two elements, gallium and nitrogen, they are bonded together in a crystal. Its band gap is like 3.4 electron volts, three times wider than a normal silicon. And that is the one difference that is changing everything, all the scenario of physics and engineering. Why? The band gap, the gap is wider. GaN can handle far more voltage before breaking down. Silicon is failing at 0.3 megavolts per centimeter. GaN holds until 3.3. That is like 11 times higher. Same size chip, every times more voltage before the materials give. So electrons also moves like about 30% faster through the GaN as compared to a normal chip silicons. Faster electrons means the transistor switches on and off more quickly. Switching speed decide how a high frequency a chip can operate. For example, a radar, 5G, satellite system all needs extremely high frequency switching. Now, here's something most sources get wrong. Some researchers say GaN handle heat better than silicon. Well, in my opinion, GaN ability is move heat away is actually slightly worse. But because the wider band gap, GaN keeps working above 200 degrees Celsius, where a normal chip fails at 150. And because GaN switches more effectively, it wastes less energy as heat in the first place. Less heat generated plus higher temperature survival. That is the real advantage. Not better cooling, but less heat and more tolerance. Well, the biggest application of this is right now ASA radar, which is active electronically scanned array. Instead of one rotating dish, it's thousands of tiny elements, each individually controlled, each steering the radar beam electronically, and every element need a chip that pushes out high frequency power without overheating. And GaN is doing all these three. So, real numbers, if we are going to talk, GaN is delivering rough 8 times the power density as compared to the older chip. It is replacing several things. For example, US Navy SPY-6 radar that is built on GaN achieved 35 times the sensitivity of the previous generation in the same physical size. And the same physics inside the GaN fast charger. The compact one replacing heavy old bricks. GaN switching power faster so the circuitry inside can be physically smaller. Same material, same physics. One protects a Navy fleet, the other charges your laptop. So the material has better numbers, but how do engineers actually build a working device from it? From all the things they have a better band gap and all this thing. Well, for example, the most common GaN device is called HEMT, high electron mobility transistor, and it works differently from a normal silicon transistor. I will tell you. In silicon, engineers inject impurity atoms, a process called doping, to force a conducting path. Well, in GaN, HEMT, they do something else. They grow a thin layer of aluminum gallium nitride directly on the top of the GaN. These two materials have slightly different crystal structure. The mismatch creates mechanical strain. That strain combined with the natural polarization of the both materials, and this is generating a strong electrical field at the boundary. Now that pulls electron into an extremely thin sheet, just nanometer thick right at the interface, and this is called two-dimensional electron gas, in simple 2DEG. Now it forms entirely on its own, no doping, no impurities injected. The electrons are like naturally trapped in a channel, so thin like they can move in one or two direction, and because no impurity atoms scattered them, they move thorough this channel like making it extremely fast. Well, this is the real engineering. The reason GaN outperforms normal silicon, not just the better material property, a fundamentally different transistor built around a quantum mechanical effect at a crystal boundary. And only a handful country can make a GaN chip right now. There is a limitation in the manufacturing. There are some countries like they are growing crystal and fabricating the finished device. For example, India became the seventh in the 2023 after DRDO spent nearly a decade building the capability independently, following the France refusal to transfer the technology during a fighter jet deal in 2016, and production was established in 2024. I remember I read. So that is gallium nitride, a band gap 3 times wider than a normal silicon chip, a breakdown field 11 times higher, electrons that move 30% faster, a transistor that builds on its own conducting channel from the physics of the two crystals sitting on the top of each other. No doping, no forcing. And another thing, 7 countries on earth can make this. Now you understand what exactly inside it. So, if you like this video, I hope if you like, I will see you in the next one.